Pietro will be telling us about representative-theoretic multiplicities and the class RBQ.
Yes, so thank you for having me. This is on the archive named as plethysms in RBQP. And there are three main questions that arises when reading the title. The first is, what is a plethysm? The second is, what is RBQP? And the third one is, why do we care, right? And I hope at least the first two I will be able to respond in a good way. So, I also am very glad that we had Igor Pak talk before me on Tuesday, I guess, because a lot of the stuff that I'm going to talk about will be will already be covered at least partially in his talk. So, but I start in a somewhat more general setting. So let's start by considering two groups, H and G, and you have an homomorphism from one to the other. And you take a representation of the big group. I will call H the small group and G the big group, even though there is no real need that one is bigger than the other. But we have a representation of the big one. And this can be pulled back to be a representation of the small one via this phi homomorphism. And what happens is that even if the big representation of the big group is irreducible, then the smaller one may not be irreducible. And in fact, in general, it isn't. And when you look at the module or the representation spaces, you can get this kind of decomposition. So you decompose in the isotypic components for the smaller group representation. And what you can do is you can very nicely pack them all up, the multiplicities, pack them all up in this kind of multiplicity space. How many times each irreducible representation appear, it's called the branching multiplicities with respect to this problem. So you have to specify, of course, G, H, phi, rho, and everything. Yes?
So just to be clear, H does not have to be a subgroup of G?
No, does not have to. So we talk about restriction, but that's kind of a little bit of an abuse of notation. Usually it's the case where the map is injective and then we can identify it as a subgroup, but it's not always the case. Okay. So there are many famous, important examples of these cases, and there are a lot relevant to algebraic combinatorics. For example, we've already seen on Tuesday Littlewood-Richardson coefficients, and Littlewood-Richardson coefficient can be described in this way by having H being GLV, and G being the product of two copies of GLV. And in this case, the map is simply this diagonal embedding when you send one matrix into two copies of itself. So in this case, you can imagine this as a subgroup, as the diagonal subgroup of this GLV times GLV. In this case, then you will have that a irreducible representation of G will be tensor products of irreducible representation of H. And you can ask how this decompose when you act diagonally on those. And when okay, so I should introduce this notation. I will use these curly brackets for the Weil modules, so for irreducible modules for GLV. And I will also write for which GLV it's here, because we will see that we will, at some point, we will have multiple GLVs. And so you want to find this one inside the tensor product of that one, and how many times that appears is exactly the Littlewood-Richardson coefficients. We also seen the Kronecker coefficient, and this you can get by the same exact construction, this diagonal embedding of one copy, this time with Sn instead of GLV, into two copies of itself. And I'll use this notation with square brackets for spec modules, which are the reducible modules for the symmetric group. Okay, so next one is the plethysm coefficient, and as you may see, it may be a bit, if you just count the number of bullet points, it's probably a bit harder, but I claim that it's in some sense the easiest case of a branching coefficient. And the reason is that here we have H being GLV, and we take the original map phi to just be an irreducible representation of H. So we map H to a GL of something, but that something is exactly such that now you have an irreducible representation. So in this sense, it's the easiest one, because every time you map H to GL of something, it's a representation, but this is, at least is irreducible. And of course, to get branching multiplicities, then we have to get a representation of G. So we have this sort of nested irreducible representations. and you want to decompose this iteration of two irreducible representation in terms of H. So just to be clear, I'll have here this second representation will go into GL of mu G, right? This is a label, and this is a representation for the G group, which is already the big group. And when you have this space, this mu G, this is already, yeah, okay. This mu G space, and you want to decompose it, then the coefficients that you get for irreducible representation of H are exactly the plethysm coefficients. Okay, so at least now we have plethysm coefficients, and the most something that you may notice is that all three families of coefficient are functions that take as input triples of partitions, because those are the labels for the irreducible representation of either the general linear or the symmetric group, and give us output a positive, non-negative natural number, I guess. And so you can define, I guess, a well-posed computational problem, at least two of them, at least, right? You can define the positivity problem and the actual computation of these functions. And you may see that there is sort of a big divide, because for the positivity problem, for the Littlewood-Richardson, this is in P. This is due to the saturation theorem, and this is non-trivial. But they managed to put it in P. And their computation lies in sharp P, and in fact is sharp P complete for binary encoding of partition, but it's not known whether it's sharp P hard for unary encoding. But it is in sharp P, so it admits a positive combinatorial interpretation in the sense that Igor Pax told us on Tuesday. And while for the Kronecker and plethysm coefficients, the positivity problem is already NP hard. So this is very interesting, because you may think that since the Littlewood-Richardson and the Kronecker at least are defined in a very similar way, and you just change the group to something that is also very close to the original one, right? GLV is the dual of Sn via the sure-while duality, in the sure-while duality sense. So a lot of times you can relate results from one to the other. But already here for the positivity, you see that there is a hard divide. And it's so hard, in fact, that we are struggling very much to put these coefficients in NP. So we only know the hardness result, we can't even place it in the class. And for the computation, and same also holds for the plethysm case. And for the computation, this is also exactly the same. You can prove of sharp P hardness, and you can prove that their membership in gap P, which is simply the difference of two sharp P functions. But you can't place this in sharp P. And in fact, this is an open problem that we heard about already, and that lies at the intersection of algebraic combinatorics and computational complexity. And to put this kind of coefficients in sharp P. And this was stated very famously in Stanley's positivity problems in positivity problem in combinatorics, something like that was the title, if I remember correctly. And stated as problems 9 and 10. 9 is the plethysm, and 10 is the Kroneckers. So this has been an open problem for a long time, and even before, of course, that paper was an open problem. And something that one may, since kind of the progress on this is slowly going on, but it doesn't really seem that we are really close to manage to put this into one of these classes. One may think, well, what if we generalize the model of computation? Since this is a problem both in algebraic combinatorics and in computational complexity, what happens when we take other model of computation? And in fact, when one looks at quantum computing, the problem was shown that for the Kronecker, you can put the positivity problem in QMA, which is the analog of NP. Or I guess it's the analog of MA, but for quantum computing, people say that it's the analog of NP. And for the computational problem, you can place this in sharp BQP, which is the analog of sharp P. And this was a very interesting result that a lot of people found interesting, especially since this is somewhat the way you do this is somewhat is very intuitive in some sense, and it really seems to show that quantum computing is the correct way to tackle this sort of problems, in which you talk about representation theory, I guess. And but the techniques that they used in that paper could not solve the plethysm case. And so what we did in this paper is we actually did the same result for plethysm coefficient. So we put both the positivity in QMA and the computation in Sharp-EQP. And we actually do much more than this. Our method generalized quite well. And in fact, we can do this for all branching multiplicities that arise from products of the general linear group. So when we take H to be products of the general linear and G to be products of the general linear, then all the branching multiplicities are already in Sharp-EQP, and there are positivities in QMA. And actually, also, if you take the symmetric group instead of the general linear, it's the same by Schur-Weyl duality. Okay. So let's now, I think plethysm are done, and maybe a bit of why do we care is also done, hopefully. But now let's look at what Sharp-EQP is. And it's the quantum computing analog of Sharp-E, okay, but what does this mean? Well, a function is in Sharp-EQP if it counts the number of accepting witnesses for a quantum computer. But of course, quantum computers don't have a discrete set of witnesses. They take witnesses as a Hilbert space. So you don't count the number of witnesses, you count the dimension of the subspace that is accepted. Of course, there is also this B, which is bounded probability, so you have to have this 2/3 and 1/3. So, but the idea is basically that you have this, this witness space that decomposes nicely as a good subspace and a bad subspace, and you want f of x to be the dimension of the good subspace. Right. And why does do branching multiplicities fit in this? Well, this can be seen, for example, from their definition, right? Because it's clear that already here they are the dimension of a space. And let's say that we want to look only at the case in which the vector lying in here is, for example, the highest weight vector in a Weyl module, then there is only one. Then the dimension of the overall subspace is exactly the dimension of the multiplicity space. So basically, thinking about Sharp-EQP just takes the definition of the problem, the definition of this branching problem, and says, can you, with a quantum circuit, actually get from this form of the witness space to a form in which that is in this basis, in which you can actually do the quantum measurements necessary to only accept if you see the lambda that you want and the highest weight vector on here. Okay, so it's somewhat clear that quantum computing is, yes?
So, I mean, is it clear that this W good should be a linear subspace? I mean, for every...
Is it clear, the thought? Sorry?
So, W good being a subspace, is that clear?
Yes, because all circuits are linear, right?
I see. Even though we're taking probability of accepting is at least 2/3.
Well, okay, so if you think about QMA, not every protocol in QMA has this nice split of good plus bad. So you're asking for a specific protocol in which you have some sort of promise of a gap between the bad ones and the good ones. And this gap of course, you can amplify it. It does not need to be 2/3 and 1/3, but it just need to be inverse polynomial, and that's already enough. But yeah, you need, this is not every QMA protocol gives you this sort of stuff. Yes, it's a promise problem. Yes. Okay, so this branching multiplicities seems to fit very well this definition, and this is a very intuitive and very natural generalization of this Sharp-E, right? Of Sharp-E and of this positive combinatorial interpretation. So before looking at how we kind of managed to do this for plethysm coefficient, let's first look at some differences between ours and previous approaches. And the first thing to notice is that Schur-Weyl duality is very powerful in this setting because it allows, well, I mean, Schur-Weyl duality tells you that these spaces decomposes in a very precise way as a bimodule for the groups GLV and Sn. GLV acts directly on each copies of V, and Sn permutes the entries. And the labels, and since they commute, they lie in each other's multiplicity space, but they are each other's multiplicity space. And in particular, the label that appears is the same in each copy, which is very, very nice. And this already gives us a way to relate multiplicities defined in terms of GLV to multiplicities related in terms of Sn. So for each construction that you can do via SN, you can also define the multiplicities in terms of just GLV and vice versa. So for example, the Kronecker can be reformulated in terms of just being the branching multiplicities of some sort of embedding involving only GLV for some V's, I guess, and etc. Okay, so this is to say that previous approaches which tackled the Kronecker and a very special plethysm case, which is the symmetric into symmetric plethysm case, so in which I guess the partitions are just the trivial partitions into the trivial partition. And this sort of approach used the symmetric group interpretation for all of these coefficients. And why did they use the symmetric group? Because for quantum computing, the symmetric group is very nice. Because, for example, you have a quantum circuit that does the Fourier transform on the symmetric group. And you have this algorithm called generalized phase estimation, which works on finite groups as long as you have a quantum Fourier transform for that group. And using these two tools, basically, they managed to decompose that witness space in such a way that they could look at only the multiplicity space and prove that this shall be KP result. The problem is that for the general plethysm case, the way to get these multiplicities coming from the symmetric group, you actually need root products of the symmetric group. And there is no known efficient enough, I guess, a quantum circuit that does the Fourier transform for the symmetric group, for the root products of the symmetric group. So this is not so immediate to generalize to plethysms. In contrast, what we did is that we shifted to the general linear interpretation of all of these coefficients, and we replaced the Fourier transform with a quantum Schur transform. A Schur transform just basically does this sort of isomorphism here. So you start with something in the computational basis of this space, and you arrive to something in this Schur basis of this space, in which is clear, in which the label is clear, the element inside this module is clear, and the element inside this module is clear. And this is a unitary map that you can efficiently, with some small caveat, do with quantum computing.
Sorry, the quantum Schur transform is the isomorphism, the Schur-Weil duality? What is the
Yes, I guess it's
another name.
it's
Full
just
name.
the Schur transform, I
It's a
guess.
full name.
Yeah.
or something.
This, I mean, you may, yeah. I mean, it's a specific isomorphism. You can define multiple isomorphisms as long as there is one for each, I guess, basis of this and of this that you like. It's a specific
Only
unitary.
the
Right?
choice of the basis is relevant.
The choice of the basis
Right,
is
you take the symmetry adapted
yes.
basis.
Usually that is relevant. In this result, is not so relevant. But yes, usually you use the Gelfand settling basis on this.
Yes, that's what I meant.
Yes, yeah. And in fact, the ones that we use does this. So
And on the left, you take the
the
monomial in a way.
yeah. On the left,
That you choose an orthonormal basis of V.
well, on the left you use the computational basis with just the tensor product
Yes,
of
computation
yes,
basis.
exactly. With just the tensor product of all the, I guess. Well, you identify V with C to the D and then the basis of C to the D. Okay. Okay. And so let's look a bit at how we actually do it. So first, some notation. Mu is now a partition of M, and mu is a partition of N, as it should be. And what we have is we have this, and we have this, and we want this to be the witness space. And we would like to kind of decompose it in such a way that we arrive at this sort of decomposition. And so that we can look at this and look if this is the highest weight vector. And first of all, look at the lambda and see if it's the correct lambda. And then look inside this and see if this is the highest weight vector. And then we only accept if we manage if both of these checks succeed. So we ask Merlin give us something that lies in this subspace, like this. And the claim is that we can actually check that this lies in there. So let's see how we do it. We start with the witness. And what we do is a very nice trick in which, well, the Schur basis of the Schur-Weil module, I guess, is made up of some element in the while module times some element in the spect module. And any element in the spect module with the same label is a good one. So what we do is we add something, we don't even care what it is, as long as it's in the correct spect modules. And we can easily prepare a state that has this property because we really don't care what it is. It just needs to have the right dimension. And what we now have is something lying in a sector, a single sector of the Schur while space. And since the Schur transforms from the computational basis to the Schur basis, an inverse Schur transforms from the Schur basis to the computational basis. So if we now do an inverse Schur transform, what we get is a tensor product of something, and that something is the defining module of the GL appearing here. And it just so happened that the defining module in this case is this new irrep for H, because of how the plethysm problem is defined, I guess because of how this is defined. And what we do, the next step, is we do something identical to this. So now we have M, in quantum computing, we have M registers, each containing a space in here. And to each of the registers, we again add an ancilla state. And this ancilla state must have, of course, the correct label. And now that we have M copies of this thing that lies in a single sector of the Schur while module, we do the same. We do inverse Schur on each of them. And this brings us to something that lies in N copies of the defining module for H, which was GLV. So this is just V to the N M. Now that we have something on V to the N M, what we can do is just do a forward Fourier transform, because it's V to the something. And this gets us back to a Schur basis for the whole module. And one may notice that everything we did is just isomorphisms that are equivalent for the action of H. Well, the first is equivalent for the action of G, but since we embed H into G via the mapping, that's also equivalent for H. And this means that by Schur's lemma, this chain of inclusions and of transformations acts as the identity. Well, first of all, it sends lambda's isotypic components into lambda's isotypic component and acts as the identity on the while module. And in part, yes.
Can you again explain the role of ancilla, please? I thought.
Yes.
On
Well,
the left, the W is the plethysm. The notation is the not. I was not sure whether I understand.
Well, this is the plethysm
This
space.
is the plethysm.
Yes. Yes.
And what is again? What is the?
Well, we interpret this as just an irreducible representation for some GL something.
Yes.
And we know that these appear in the Schur while decomposition for
right.
some vector spaces, some vector space.
But what is this a map or what? I don't. What is the add ancilla? What is
Okay, in quantum computing terms, you have a register and you have you add another register which contains something lying in this space. So you add it in such a way that there is no entanglement. You just have two things, right? You produce a state that of the right dimension living in here, and then the next transform you will do to these two states simultaneously.
It's something you pass from something to.
I mean, mathematically.
I add sugar to something.
Yes, mathematically it's a map. It's an embedding. When let's say you choose an element in here,
you have to choose.
And then you simply tensor by that.
You have to choose on the right hand side something.
Yes, you choose something on the right hand side, and then you tensor by that. And this is an embedding, right? Isometric embedding. Yes.
It's an embedding. Okay, it's an embedding.
Yes. So you just add another thing, and
why you do this? I mean,
because so let's go. Yes. So if you look at the Schur decomposition, this says that a sector in here looks like something times something that has the same. And the Schur transform, the quantum Schur transform, is a unitary map from something that looks like this to something that looks like that. The inverse of this unitary takes as input something that looks like this, so two spaces, one with the same label, one for the unitary group and one for the unitary or general linear, it's exactly the same in this context. One for the general linear, one for the symmetric group, and it will give you back, this unitary will give you back this expression, but in terms of this of the computational basis of the space. Right? This is the unitary that maps. It will give you the coefficient of these things in terms of the unitary, and now you have these quantum states in which the amplitudes for each thing will represent. You've basically done this change of basis. Now you have states that are in this basis of the state of this space. So the reason you add this is that the quantum short transform to work needs something in here and something in here, because otherwise it's not an isomorphism, I guess. Of course, by the end, the choices that you made here and here, right, will be respected in which part of the multiplicity space, which is the spectrum module you are. So what you did is the identity on the divide module, and you had an embedding from the multiplicity space to the spectrum modules. And this embedding is uniquely determined by what choices you made here and here. And this embedding can be very hard, but you really don't need to know in what subspace you lie in here. You just need to know that this is isometric from here to here, and that preserves this. At that point, if you were to actually measure and look at lambda, you know that the state that Merlin gave you must have been in lambda. And if you were to only accept if you look at the highest weight space in here, then it means that you're only accepting a state for this dimension subspace, which is exactly what you want to prove SharpBQP. So basically what we do is we do this two-step procedure in which the embedding is everything but the last arrow, in which we embed this plethysm space into this V times NN. And then we do this measurement state in which we want what is called we do strong sure sampling, which just means that we look at both the label and a vector inside here. Okay, and this is the circuit if you prefer the circuit, but it's basically the same. We have a witness, we add something and then we embed, we do this inverse Schur transform, we get a lot of stuff, to each of them we add something, and then we do Schur transform like this, and this is the embedding step. And for the strong Fourier sampling, we just use a Schur transform. And it just so happened that to do both of these steps, we only need to use one sort of primitive operation, which is this forward Schur transform. But this, of course, can be generalized to such setting in which this you do in whatever way you like, and this you also do in whatever way you like. Okay, so overall, this is a projective measurement onto the multiplicity space. I think I should be quicker. Then there is a challenge, but also a solution. And the challenge is that historically, the quantum Schur transform, which is the only primitive that we use, was very inefficient in the local dimensions. In fact, it was polynomial for C to the D tensor n, it was polynomial in D. Recently, very luckily, people have improved this. And in fact, they managed to get it down to polylog D, which is exactly what we need, because for the first step in this circuit, for this inverse Schur transform here, in fact, the local dimensions are exponential in the input sizes, and the inputs are just the partitions, I guess. Okay, so this is just a summary of the result. We do this for the generalized plethysm problem. And we also develop a generalized framework, which works for all the things that you can get via this only Schur transform stuff, which is all products of general linear groups and symmetric groups. Of course, in this example, we have Littlewood-Richardson and Koska, which are known to be in Sharp-P, so it's not relevant. This result per se is not relevant, but it's just to show that the class that we extend this to contains a lot of interesting stuff. And here are some future directions that could be interesting, and one of them is especially interesting to investigate the relation between SharpBQP and these two classes, Sharp-P and Gap-P, because it's not even known whether SharpBQP is in Gap-P, which is somewhat surprising. And then SharpBQP, SharpBQP is sort of a two-step generalization of Sharp-P. The intermediate step would be SharpBPP, and this is also kind of an interesting question, whether you can put these sort of coefficients in there. and also whether this would count as a combinatorial interpretation, because at least in this case the witnesses are classical objects and not quantum states. And then whether we can use this sort of approach to actually compute these quantities, and whether we can get some speed up. There are some partial results then in which there are some polynomial speed ups that seems promising. And that's all I have for you today. Thank you for having me.
Questions?
Can you go back to the slide with the wreath product?
Yes.
Because I don't think I understood the statement. So, the prior approach, you say, so I'm confused by the statement with the wreath product, because the prior approach has a wreath product in there, and
Well,
sort of the thing. So what's the statement?
The statement is that Fourier transform for wreath products are only efficient in very special cases.
So you say in this case it's
This is a special case, yes.
it's a special case. So but what will happen, so it seems to me like the classic, this what you call the prior approach,
Yes.
would just work when you just tensor with before doing the invariant space, just tensor with a spec module, and then you would get the more general plethysm coefficient. So I don't see
But
what the issue here is that you're solving in a completely different way.
sorry, could you repeat
So-
your approach?
So the plethysm coefficient, I mean, you take this wreath product invariance, yeah,
Yes.
and you get the more general plethysm coefficient by first tensoring with the spec module and then taking the wreath product invariance. So it seems very, very similar. So I don't see what the big issue would be here to just take the prior methods.
Well, the prior method requires, if you use wreath products of the symmetric groups,
I see.
in order to do that, it requires to have a quantum Fourier transform. Otherwise, it doesn't work.
And then you can, okay.
Right? To do this generalized phase estimation, it's what allows you to decompose any module, basically. But in order to do that, you need to have a Fourier transform for the whole group.
Okay.
And if you don't have that, then you. But there is some hope of getting an efficient Fourier transform for the wreath products of the symmetric group. So that's a good news.
I have a question to what you told us at the, I think it was almost the last slide where you said it's now important to have an improved quantum Fourier transform where E is replaced by
Yes,
C
this.
from Burkhardt. Can you say something about this? Or just
Yes.
to have a rough idea what's
Yes. So
behind this?
actually, this is a very interesting topic because there are at least two different ways to do this. And the first way was kind of sketched. So the typical approach to quantum Schur transform algorithm is called this BCH quantum Schur transform. And one of the authors, Aram Harrow, which was also an author in this paper, actually in his PhD thesis sketched a way to possibly make this original quantum Schur transform be only logarithmically, the polylog dependent on this local dimension. But this was just sketched without any details. And for a while people cited this, but without actually doing any of the calculation and looking if it actually works. Then there is a second, and this approach is basically, this BCH approach to the Schur transform is basically you do this Clebsch-Gordon product for single boxes until you arrive at the full n boxes. And then you do it one step at a time, and in the end you arrive at this Schur basis, this Schur-Weil, this Gelfand-Settling basis for the Weil modules and for the symmetric group module. But there is another approach to get a Fourier Schur transform, which was originally taught by Harry Crovey, but it was later found to have a mistake, and that was also logarithmically dependent on this. And it does it in a completely separate way. It does it more so from the side of the symmetric group. And basically this paper, this Burchard et al. Paper, they do it they managed to correct both approaches because both of them were quite unsatisfactory from how they were in the literature. Because one had a mistake and the other was just sketched and told without any proof.
Is there, I don't know, is there any relation to,
Okay.
I'm thinking of Fourier transform.
Maybe
Okay,
take
I'm
this
not
offline.
that,
Should we take this offline?
Yes.
okay, we can take
Yes.
this offline.